My name is Daniel Volpe. I'm a computer science student at UCF, and I'm the project manager of Adiona.
Hello, my name is Dylan Burns, and I am a computer science senior at UCF.
My name is Jacob Sage, and I'm a computer science major, and my role in this project is computer vision.
Good morning. My name is Alexander Davis, and I am the resident mechanical engineer on the Adiona project.
Hello, my name is Lauren, and I was responsible for motors, electronics, controls engineering, and our website.
Hi, my name is Charles McCampbell Hill, and I've essentially been working on the software aspect of this project. I have been heavily involved in integrating Nav2 into our robot so it can autonomously navigate.
Our objectives were pretty clear when designing Adiona. We needed to design a rover that could withstand the launch of a rocket, parachuting back down after a 10,000-foot apogee. We needed to reach the ground, then open its canister and autonomously navigate back through the desert for a range of about a mile, back to the launch site, and all the while it needed to provide live video footage.
So for this project, we're building an autonomous rover, and with that comes softwares like the Robot Operating System and Navigation 2 package. So for the Robot Operating System, we chose to go with the second version of it, ROS 2, because it includes the Data Distribution Service, which is a way that we can manage the nodes in the background via RAM without having to worry about the system going down and having to restart the nodes in case of any hardware failures. The way that ROS is built is a publisher-subscriber system, where we have a publisher publishing messages to a topic and a subscriber subscribing to those messages via the topic. The publisher and subscriber are both nodes within the ROS system, and topics can be easily listed via the terminal. For this project, we're also using the Navigation 2 package. This is because it allows us to use the SLAM technology, simultaneous localization and mapping, to seamlessly map our environment and decide where we are within that environment. Along with this, we are using GPS to decide where we are and where we need to go.
Oftentimes, a straight line isn't the best path for the rover's recovery, even if it can avoid obstacles along the way. So, a waypoint generation system is used on Adiona in order to have Adiona route around large sections of land that might have heavy amounts of brush or be harder to traverse than other pathways.
My role in this project is object detection, and to address this, we equipped the rover with an OAK-D depth camera as well as a LiDAR system. The LiDAR system will be placed on top of the rover and consistently spin to capture object data and distance values. The OAK-D camera has a stereo camera on either side of it for calculating the depth and distance for any pixel that we desire in the input image, as well as a 4K camera that is in the center to efficiently detect objects using neural networks. With the combination of object detection and distance values, we are able to replicate LiDAR data in the event that it ever fails.
Hi. So this is essentially how our software is going to work. This is a flow chart indicating which part is going to be connected to which. So initially we begin with IMU and odometry. So IMU data will be initially captured using the IMU within the OAK-D camera. We currently have a publisher to take data from the IMU and publish it to the ROS 2 topic. And then odometry will be captured from the wheel encoder within the motor, which will then be passed to the robot localization package, which will use an extended Kalman filter to blend both the IMU and the odometry data together, which will be published to a topic that will be combined into the transform data, which will tell us where our wheels are and where we are, the odometry filtered data, which will tell us how far we're moving, and the map data, which will be gathered using the 360 2D LiDAR unit that we have on board. And all of this information will be passed to Nav2, which takes all the data and uses a planner and a controller to devise a path using our given movement method that will give us velocity commands. And then once we have these velocity commands, we need to then decompose them into a velocity command itself for forward and backwards and a steering angle, which will then be given to our robot, which will then turn the wheels a certain angle and move us in the right direction. Now, because of the planner we have, it will take into account the fact that our robot has a servo for steering and just forward and backwards velocity commands. So once we decompose them, we'll be able to move efficiently and in a quick manner.
Given the current state of the world, we've had to use a lot of online methods to connect with each other. This includes Discord, which is a house for our public communications where we have multiple channels for software, hardware, meetings, and other objectives for the rover. We're also using Zoom and Teams to connect with our other teammates and to have calls with our coordinator and supervisor, Dr. Sotatoro. He is helping us greatly by giving us input on how we should approach these tasks incrementally and help us complete our Gantt chart. And we are also splitting into hardware and software teams, as previously mentioned, so that the software team can tackle the simulation of the rover, while the hardware team can build the physical unit, which will later be integrated with the software that was previously simulated. Now, no big project like this comes without its challenges. Some of the challenges that we faced were budget. You see, we were initially told that we would have less than $2,000 to spend, so we decided that our feasible amount would be $1,000 to cap ourselves at. This tended to be a little bit of an overshoot, and we ran out of money for procurements before we thought we would, so there were some drastic changes to the hardware, but the hardware team has been great and has accommodated to those issues accordingly. But to overcome this, our hardware team has done a great job of CADing up designs in their 3D software and 3D printing at home, and relentlessly producing many different iterations and versions of the rover.
One of our main design challenges on the mechanical side was part procurement. We budgeted our original rover design to about $700, and after we had spent about $400 this semester, we were informed that we were out of budget. We had not gotten any of our significant drive components, especially the motors, yet, so we petitioned to get at least two. They approved our petition, and when we went to pick up our parts this week, we found out we only had one, and the one that they gave us was broken. So not only did we have to, as we were receiving this information, change our design from a 4-motor, 4-wheel drive rover to a 2-motor 4-wheel drive rover, and then finally to a 1-motor 4-wheel drive motor, but we had to start looking into getting our own motors from other sources. I had to pay out of pocket for myself. I had to get parts from old electronics at thrift stores and really scavenge as much as I could to kind of put our rover together with the parts that we had.
One of the design challenges our team was asked to take on was having our rover travel over a mile to return to the rocket's launch site. This meant that we had to have enough power to supply our motors, sensors, computing hardware, filming, and transmission for an extended amount of time. To do this, we needed to maximize our electrical efficiency and our usability for our software team, while minimizing our gearing to decrease resistance. We're overcoming these obstacles by using a brushless motor with an advanced motor controller called an O-drive. Brushless motors are 50% more efficient than brushed. The motor's kV rating describes its RPM per volt, and since we need our rover to move slow enough for the software to process its environment, we chose a motor with a lower kV rating at 1900. Although this is still somewhat high, the advanced control systems on our EOC gives us the ability to have precise control over our current input, velocity, and positioning. We just need to be careful in configuring our gains to ensure we don't accidentally send more RPM than we'd like during our PID loop. It also uses regenerative braking, sending excess power back into our battery instead of it dissipating as heat.
We were motivated to see this project through to completion, despite all of the struggles we had to endure, because we hadn't created anything like this before. We were using our degrees, but we were also learning so much, and the whole team had a strong desire to see that vision actualized as a rover on the ground.
With regards to broader impacts relating to this project, a rover that can autonomously navigate from one point to another certainly has applications in the space industry. With the billionaire space race fully in effect, planetary exploration will soon become much more frequent than it is today. With that, an affordable and reproducible rover that is capable of navigating and exploring the unknown that is in front of new inhabitants of planets is an excellent tool for safety and exploration. I'm sure each team member has their own reasoning for why they would want to work on an autonomous rover, but the motivation personally is that as a computer science major, we do not get to work with hardware often, and thus I jumped at the opportunity to learn a new skill. Along with this, the autonomous vehicle is a growing industry, and learning object detection personally was a very valuable skill that I can apply to more than just one area of my career.